The lathe has sometimes been referred to as the queen of the shop, and that's with a good reason, because it's a very versatile machine. Any spindle machine, such as a drill press or a milling machine, takes a cut that can be duplicated on the lathe. In fact, the lathe predated most other machinery, and things like milling machines developed because of what was learned in running lathes and using them. The lathe is a very old form of machine tool, and the specific lathe that I have here is quite an old one in its own right. It was built in 1941. It's a South Bend Model B. It has a 9-inch swing, and it's the short bed model. It has power longitudinal feed, and it has power cross feed, all of which are controlled by gearing, and we'll show you more of that later on. The discussion that we're going to have today relates specifically to this lathe, and some of the things that are on this lathe as its features will be a little different from the lathes that you may be running, but the principles are the same, and whether you're running a larger machine or a more modern machine or a micro lathe, the things that we're going to discuss today will apply to your lathe, and I believe that you'll be able to learn from them and apply them to your work. Now, there are three principles which must be learned in order for you to do good work. The first is that the workpiece that you put in the lathe has to be very solidly supported. You can't have it loose because you're going to get into trouble. When you cut with a tool in a lathe, it's a heavy stress. The work must be solidly supported. The lathe must be running at the proper speed, and the speed at which the lathe is run is determined by the size of the work, and it's determined by the type of metal that you're cutting. The third thing that has to be met, the third condition, is that you must have a sharp, properly shaped tool positioned properly in the lathe and presented against the work. Only the cutting surface of the tool should touch the work, and there should be no other contact between the tool and the work. This will provide you with a clean cut, provided you're running the lathe at the proper speed and that the work piece is solidly mounted. All of lathe work really comes down to three operations. The first is turning, the second is facing, and the third is boring. When you take a turning cut in the lathe, your tool travels in this direction across the lathe. You may be cutting toward the headstock, which is usual. You may be cutting toward the tailstock. But whichever way you're cutting, you produce a cylindrical workpiece, something like this axle that I have in my hand. The second form of cutting that you do in the lathe, which is facing, the tool travels across in this direction. You normally begin a facing cut at the center and work toward the outside, and you produce flat surfaces like this disc. This is a little disc, a piece out of a machine, which was faced off smoothly and flatly, beginning at the center with the tool working its way out. The third form of cutting is boring, in which the tool travels into the workpiece as it rotates. The tool cuts away the metal on the inside and leaves a hollow cylinder. The truth is that most lathe work, because it's complex machine parts, involves several different steps, and it uses all sorts of cuts. On this adapter, for instance, you can see that there was a facing cut on this surface, there was a facing cut here, there was a facing cut here, there was a turning cut here, turning cut here, turning cut here. There was a facing cut on the back side. There was a boring cut inside from each end, a different size. You'll notice that there was also a thread cut internally. And when you're cutting internal threads, this is actually a variation of the boring operation. When you're cutting threads externally, if this had been threaded, for instance, that would be a variation of the turning cut. So all of the cuts that you take on a lathe come down either to turning, to facing, or to boring. And if you get a complex workpiece, such as this spindle, which is out of a drilling machine, you can see that it has had turning cuts in several places. It's had a threading cut on the outside, and here we have another form of cut, which is also a turning cut in that a taper was cut. It's had a facing cut here, it's had a facing cut here, and on the far end it's also had a facing cut, and this one has also been in a milling machine to cut the splines, but that has nothing to do with the lathe, so we're not going to discuss that for today. But there's a very nice combination of lathe work involving turning, facing, and the turning operation of putting the thread, the turning operation of putting the taper. The final thing that you can do on a lathe, which is also a variation of the facing cut, is to put a tool on to do cut-off work. If you've been turning a short piece and you want to cut it off, you can put on a special tool, advance the work across the cross slide into the work, and you will cut it off. And I'll show you more of those tools in just a moment. The first principle of good lathe operation that we discussed was the fact that your work has to be properly supported, which means that it has to be held in a solid position as it rotates so that the tool can remove metal from it. One of the simplest ways of doing it is with a 3-jaw chuck. This is a 5-inch 3-jaw, and on this particular machine the chuck screws directly onto the spindle nose. On some more modern lathes they don't screw on this way, they have cam locks, or they have threaded back plates, or they have other means of attachment. But on this machine, this is the way that the chucks go on. When you use a 3-jaw chuck, it's a very quick tool to use. It's self-centering. As you turn the key in the screw, all of the jaws move at once. It will center and hold a piece of work quickly, but that's its main advantage, that it's quick. It's not an extremely accurate method of holding the work. A good chuck will hold work within about 5/1000ths of an inch, but when chucks begin to get very old, as this one is, they begin to wear and become bell-mouthed because the scroll wears and the jaws become stretched, and you can't depend upon them so much for accuracy. In that case, the most accurate form of chuck that you can get is a 4-jaw chuck. The 4-jaw chuck that I have for this machine is a 6-inch chuck, which is about the right size for a 9-inch lathe. And this one also threads directly onto the spindle. And it holds whatever workpiece you put in it. Now, there are a lot of advantages to using a 4-jaw chuck. To begin with, the way it works is that each jaw is independently moved. When you take your key and put it in, only one jaw moves at a time. This means that if you have an irregularly shaped piece, you can move the jaws in a way that they compensate for the irregular shape. It also means that if you have even a very regularly shaped piece, you can put it in. If it happens to be a little bit off center and you want it to be adjusted to an exact position, you can slack off on one jaw, tighten on the opposite side, and you can shift the workpiece around until it's exactly on center as you want it. The 4-jaw chuck is slower to use. Some people find it tedious to bring it into position, but I must tell you that if there is only one chuck that you can afford, the 4-jaw will do every job that the 3-jaw chuck can do, and it will do more besides. If you want to hold work very accurately, collets do good work also. Collets are somewhat limited in size, and you have to have several of them. Each collet will hold only one specific size, and the work that you put in it can't vary by more than a few thousandths. In other words, if you put in a 3/8 inch collet, it has to be, the work that you put in it has to be within about 5/1000ths of 3/8 diameter. When you put collets in, you thread on the nose piece, you put in the collet closer, and you slip in the appropriate collet for the job that you're doing. You put in the drawbar, which threads onto the back of the collet. It pulls the collet in, there's a taper inside, and as the collet is pulled in, the jaws close and they hold the workpiece very securely. They hold the workpiece very accurately. As long as you don't stretch your collets or do damage to them, the collet is probably the most accurate chuck type of holding device that you can obtain. It's possible to do some other things with chucks, and I'm going to show you something that I have done here, because I tend to build small engines and do work which is fairly small in size at times. Here I've put in a collet which is for 1/2 inch, and I've made a special small adapter to go on the back of this little chuck so that I can put a little small chuck in here. And it's held in the collet, and that allows me to handle some very small work pieces so that I can get the tool in closer, even though I'm working on a rather large lathe. So far we've talked about using chucks on the spindle of the lathe for holding work. There's one other job that a chuck can do, and that is to hold drills and to do center drilling and other drilling with twist drills. When you do that type of work in a lathe, you normally put a chuck on an arbor into the tailstock. This permits you to hold center drills or other twist drills or reamers, so that when you're making holes on a workpiece which is in some other chuck or whatever way you're holding it on the headstock, you can put it in and advance the tool into the work as it rotates. The tailstock chuck is very seldom used to hold work. It's normally used as a part of a cutting tool, and it's used mainly in drilling operations. While chucks can hold a lot of work which is either regular in shape or irregular in shape, there sometimes come jobs that you can hold best on a faceplate. The faceplate mounts on the lathe spindle, whatever the mounting method may be, just the same as the chucks do, but it provides you with a large flat surface. This is a useful form of tool because the faceplate is always made with some sort of slots in it. Sometimes it has holes in it. I have some holes in this one which I drilled and tapped for special jobs. And it allows you to put clamps and bolts through the slots or through the holes that you make in it to clamp work to it. For instance, if you had some kind of a big flanged bushing, you could bolt it onto the faceplate, center it accurately, do whatever you have to do, and do your boring cuts or turning cuts or facing cuts, whatever is necessary, and you could do that on the faceplate. The faceplate doesn't have to be a large one like this. This one is really up to the full capacity of the lathe. They may be small also, like this little faceplate. Now this is a special faceplate because you see it has a slot in the side. I've drilled and tapped some holes in it for bolting work to it, but this slot is what makes this one special. It's called a catch plate, and I'm going to show you how to use the catch plate too. The catch plate is used when you want to drive a piece of work which you mount between lathe centers. This is one of the solidest and most accurate mountings that you can make. The way you do it is to put a large center in the headstock of the lathe, and you screw the catch plate in. Now you put another center in the tailstock of the lathe, and if you have a workpiece which is shaped like an axle, you can mount it between the lathe centers. And in this way it'll run very accurately. Now there's one thing more that you need when you drive work in that way, and that's called a lathe dog. The dog is a driving device which clamps on the workpiece. In this position, it clamps to one end, And you can see that it has a tail. That's why they call it a dog. There are bent-tailed dogs and there are straight-tailed dogs. And when this goes between the lathe centers, the tail engages the slot in the catch plate so that as the lathe spindle rotates, it drives the workpiece around. And you can work on it to take turning cuts or facing cuts or whatever you need. There's one other form of holding work which is important to consider in lathe work. Sometimes it happens that you have an odd spindle like this, which is out of a drill press. You have to do some turning work on this taper because this taper has been scarred. It has to be worked on. You mount it in the chuck. It has such a long overhang that you can't do the work. This shaft is likely to bend, or it's likely to get whipping around, or it will chatter. It will do most anything. In a case like this, you have to support the work on a steady rest because you have no way to support it from the outer end. You can't put a center into it, and you can't support it adequately from the chuck. So you put on your steady rest, and this bolts fast to the lathe bed by means of a bolt coming from underneath, and then you advance the jaws so that they support the work securely. After bolting the steady rest firmly to the lathe bed, you can adjust the jaws and tighten them in position. The point being that they contact the work at a point where it's solid. You tighten these up, and of course you tighten everything much more securely than I'm doing it now. But now as the work rotates, it's held between the jaws of the steady rest, which act as a bearing surface on it, and they hold everything solid so that I will be able to work on this taper out here to improve it and set the machine right. Now you'll remember that the third principle of good lathe operation that we discussed was that you have to have a properly ground, shaped, and sharpened tool which you present to the work in a rigid way. There are several ways that we can do it. One of them is to use an open-sided tool post. This is a European type of tool post which mounts on the compound slide by fitting into the slot. Once you put it in, you put the tool to the position you want and you tighten it. Now this is called an open-sided tool post because it has a single open slot on the side. This is a very rigid, a very solid tool post. It will hold the tool securely. It's capable of doing the very heaviest types of cut. I want you to notice that I have a diamond tool holder in it. This is a tool holder which is made in Australia. It holds the lathe tool tangentially. It's capable of doing turning cuts or facing cuts, or if you grind the tool properly, it's capable of doing threading cuts. This is a very useful form of tool holder, and this is a very useful and solid form of tool post. Related to this European style tool post is a turret. Now I have a turret here. The turret slides into the compound rest in the same way. When you get it in, you tighten down with this nut, and you can see that the turret is an open-sided tool holder also, but it's open on four sides. As you turn the handle, you can turn the turret. It allows you to insert four different tools so that you can take repeating cuts going from tool to tool. I only have two tools in the turret at the present time, but it can hold four, and of course once you turn a tool into position, you lock it down and it's secure. These are very accurate instruments because each time it turns, it has a set of ball bearings in the bottom that position the tool exactly, and you can depend upon this to index your tool into a proper position when you lock it down tightly. The third form of tool post and tool holder that you're likely to encounter is the American style. Now the American tool post is sometimes called a lantern tool post. The reason it's called a lantern tool post is because of its shape. This part is the tool post. It slides in, and this is the tool holder, which goes into the tool post. This tool post has a rocker in it so that you can shift the rocker back and forth and change the position of the tool, and when you get it where you want it, you tighten it down. Now you'll notice one thing, that in this straight tool holder, the tool is turned upward at an angle of 7.5 degrees. This is an important consideration because it takes a little of the rigidity away from the American tool post. It's not quite as solid as the European style. Furthermore, to use an American tool post properly, you really need 3 tool holders. When you view them from the top, this is a straight one, this one is right-handed, and this one is left-handed. These allow you to reach a variety of shapes and positions while you're doing lathe work, whether it be for facing or turning, although none of these tools are useful for boring. When you get into boring, you have to have a special holder, such as this one. This is quite a heavy-duty boring bar holder. You see it holds a round steel bar, and the cutting tool is this tool, and you use this by advancing this into the work. In fact, the job that we do today is going to be to make one, and the one that we're going to build will be like this one. This is a smaller one, a little bit lighter duty than the one I just showed you, but a very versatile all-around boring tool holder. It's able to hold a small bar like this one, which permits you to reach inside of holes that are only about a ½ inch diameter, or you can put in a heavier bar. It's made to accommodate either one, which will allow you to do boring cuts up to about 1.5 inches or so in diameter. The final operation that you're likely to encounter in doing lathe work is cut-off work, and this is a variation of a facing cut. This is a cut-off tool, the way it's bought. It's a special form of tool. You can see it's very thin and very long. The holder that I'm using here, the tool post, is also a home-built one. It mounts on the compound rest in this position, and it's truly a facing cut because as you advance the tool into the work, you cut off the metal piece as it rotates, and it's a specialized type of tool and a specialized type of operation. We'll discuss the conditions needed for that in a little more detail later on. The second principle that we discussed concerning lathe operation was the speed at which you run the lathe. Now I want to discuss to begin with what the speed of the lathe means and how you determine what you're going to run. With your tape you received a chart which is a reproduction of this one. It's in a smaller size, but this is the same chart, and on the top part of it here you see the cutting speeds for turning or boring with high-speed steel cutter bits. These figures are all expressed in surface feet per minute. The cutting speed is determined entirely by the kind of metal that you're cutting. I've listed several metals: cast iron, mild steel, stainless steel, free cutting brass, yellow brass, bronze, and aluminum. Each one requires to be cut at a particular speed. For instance, with cast iron, you want the surface speed to be 60 feet per minute. With mild steel, you want it to be 90 feet per minute, and so on. What this means is that this is the speed at which the workpiece should be passing the tool. This is not a rotational speed. This is a linear speed in feet per minute of the surface going by the tool. Now, how do you convert this into a usable spindle speed? You do this by relating the diameter of the work to the surface speed. On the lower part of the chart, I have expressed this. You will notice on the lower part of the chart that the heading says spindle speeds for turning or boring expressed in RPM or revolutions per minute. I've listed work diameter in the left column, and I've covered a range of 1-inch diameter all the way to 12-inch diameter in 1-inch increments. In this direction, I've listed 50 feet per minute, 100 feet per minute, and 200 feet per minute. So, in order to use this chart, if I select some metal, such as aluminum, which cuts at a surface speed of 200 feet per minute, I can look in the 200 feet per minute column, pick off the size of the work. For instance, if I'm turning a 6-inch pulley in aluminum, I go across to 200 feet per minute, and I find that it should be running at 128 RPM. Or if I take some other metal, such as cast iron, which runs at 60 feet per minute, the closest to it is 50, and say I'm turning a 3-inch piece, 64 RPM, or a little bit more, maybe 75. Now, bear in mind that these figures are not exact figures. They're suggested figures. They give you a point from which you can begin to work, and you can interpolate and you can extrapolate. You may find that your lathe doesn't give you exactly these speeds when you're turning a very large piece, for instance. A 12-inch diameter piece of cast iron, you may not be able to get your lathe down to 16 RPM. Well, in a case like that, you do the best you can. You come as close to these figures as you can, and you will probably find satisfactory operation. But you must bear in mind that even from one piece of mild steel to another, or from one piece of cast iron to another, you will find differences in the metal you're cutting. So you use this chart as a guide, but you also use your head at the same time, and you make the corrections. One thing that I would have to say is that these recommended figures should be taken at the beginning as maximum figures. If you have to change the speed at which you run your lathe, it's preferable that you run it more slowly than more rapidly, because when you run a lathe too rapidly, you are likely to develop a chatter pattern or get into some other problem. The problems that arise with chatter and the other things that happen in a lathe, they may be a worn lathe, an old machine, can't take quite as much speed, you run it more slowly. And I don't mean a small change in speed. I don't mean that if you have selected, let's say, 382 RPM and it begins to chatter, you don't slow it down to 375 and say that's adequate. If you're getting a chatter at 382, you cut it down to 200, or you cut it down to 150 and see what happens. And bear in mind that these figures are for high-speed or alloy steel tools. If you run carbide tools or ceramic tools and your lathe has got the strength to withstand it, you can run at much higher speeds without overheating the tool, and you'll be okay. These figures apply to turning cuts, to boring cuts, and in general they apply to facing cuts, but you realize as you take a facing cut, you'll begin the cut at the center, you'll bring the tool out, the diameter of the workpiece is changing continually, which means that the speed at which the tool is cutting is changing continually. In that case, you take some median value and you work with it the best that you can. If anything begins to go wrong, it doesn't look right, slow the lathe down. We discussed taking a cutoff a tool and putting it on to do a cutoff work. Cutoff work is always done much slower than this chart indicates. You see, this chart specifically says that it's for turning or boring. It's not for cutoff work. In doing cutoff work, you generally drop your lathe to its lowest speed or somewhere near it. If you're running a very small piece and you're cutting it off, you may be able to run it a little faster, but cutoff work is always done at much lower speeds than turning or boring. Now, I've emphasized from the beginning that there are three operations that you can do on a lathe, which are the fundamental operations, which are turning, facing, and boring. And in order to practice the facing and boring cuts, we're going to put in a project of making a boring tool holder. Only facing and turning cuts are required to make the boring bar holder and the boring bars that go in it. But once you get the tool made, you'll be able to do boring work, and I'm going to show you how to set it up on the lathe and do that. With your tape, you received a set of drawings, which included the chart of speeds and so on, but they also included the drawings of the parts of the boring bar holder and the boring bars. The parts that have to be made are relatively simple. They consist of this clamping plate, which is this part on the drawing, the clamping screws, which are this part. These don't require any lathe work. You can cut the plate by hand and you can file it by hand, or you can mill the edges if you have a milling machine. The important thing is that it be able to slide into the slot on your compound rest freely so that you don't have to struggle with it. The parts that require lathe work are the boring bar holder itself and the boring bars. This is the boring bar holder. I have a set screw in it that holds the boring bar in position. It's this part on your drawing. It has to be faced off on each end. It has to be turned. And finally it has to be drilled in several locations, and it has to have a tapped hole in the top for the set screw. But these are operations which will give you an opportunity to practice turning and facing cuts on your lathe. The boring bar itself that I have in my hand is the small bar. The small bar is the one at the top, and the larger bar is the one at the bottom. These are simple turning and facing operations also. Each one has to be faced off on the end. The smaller one has to be turned down to give an area that will reach into relatively small holes. The larger one does not have to be turned down. You can make this from 1/2-inch diameter stock steel rod. And each one has to have a little groove machined in it so that the set screw, when it tightens down on it, doesn't scar it. But these are simple operations, and I'm going to demonstrate to you how to go through them so that you also can make this boring bar holder and do boring work on your lathe. Okay. Before beginning on the actual work of making the boring bar holder, I think we should pause for just a moment and look at the lathe itself to identify what its controls are and what they do. In order to present the tool to the work and take a turning cut, it's necessary for the carriage to travel either toward the headstock or away from it. This hand wheel moves the carriage in either direction depending upon how you turn it, but this is a coarse feed. This is not a feed that you normally use. This is normally gear driven, and that's what these handles are for underneath. When I swing this handle up, it engages the gears in the saddle of the lathe. When I tighten the clutch, it puts everything into a position where the carriage will travel under power feed and make the cut. On this particular lathe, I can do the same thing for the cross feed, but in this case I can turn this handle to move the carriage in or out toward the center. By moving this handle down to the lower position, I've engaged the mechanism in the apron. When I engage the clutch, the gears that are up in the headstock of the lathe will move the carriage back and forth under power feed. This part of the lathe, which is known as the cross slide, may be controlled by turning the hand wheel, or on this particular lathe I can swing the handle down to its lower position and tighten the clutch, and the gear train in the head of the lathe will automatically drive the cross slide in either direction depending upon how I set it. The final movement that you have is this compound rest. Normally this is set the way I have it here, parallel to the axis of the lathe. As you turn this hand wheel, you can move the compound rest in either direction. But the compound rest is adjustable, and you must be careful as you set it to be sure that you are getting it parallel. You can do something else with it which is quite important. You can turn it at an angle like this, for instance. And when you tighten the screws and move it from here, you can see that the tool would be moving at an angle. This is one of the ways that you can machine tapers on your lathe. When you machine a taper, it's really the same cut as a turning cut, but it's made at an angle. And it allows you to fit pieces which will go into the headstock or into the tailstock in the taper joints, or if you happen to have a need for tapers for some other purpose. The gears that control the movement of the carriage of the lathe longitudinally, either toward the headstock or toward the tailstock, and the gears that control the motion of the cross slide, either toward the center or away from the center, are housed under this door on the end of the lathe. You'll notice that there's a pinion gear here, and this is directly on the spindle of the lathe. As the lathe spindle turns, that gear turns at all times. There's a cluster gear below it, which drives down through a second pinion to a train of gears that moves the lead screw. As the lead screw rotates and you engage the clutch and the mechanism in the apron, that's what imparts the motion. Now there are two ways that you can set this cluster gear. You can set it forward or you can set it backward. When I put it in this direction, it's set for forward running, and when I engage the clutches, both the longitudinal travel and the cross travel will move in the preferred direction. When I set it in the opposite direction, I can reverse the direction of rotation. And this is important because these are the motions that permit cutting either left or right-handed threads on the same gear, on the same lathe. Now this also can be locked in a neutral position, and when it's locked in a neutral position, there's no motion imparted. All of the controls become manual. There's a second set of gears in the lathe, which are called the back gears. They're behind the spindle at this location. The reason for the back gears being there is that when you engage them, the spindle runs much more slowly and it has much more power. When it's in direct drive, as the lathe is at present, the motor, which is on the countershaft mounting behind it, drives by means of a pulley to the countershaft, and then there's a belt which comes directly from the cone pulley on the countershaft to the cone pulley on the lathe spindle. And as you can see, when I go in direct drive, the spindle rotates quite fast. Now when I put the lathe into back gear, it'll go much more slowly and have much more power. There's a little clutch pin, it's a driving dog on the bull gear up here. I pull that out to disengage the clutch, which frees this pulley on the spindle, and then I engage the gears. Now the back gears are fully engaged. This pulley is freed from the spindle, and it's driving through the gear train to drive the chuck. And as I turn this on, you'll see it go much more slowly. In this condition, if I have a very large workpiece where I need low speed rotation, I can obtain it. Or if I have an extremely heavy cut where I need a great deal of power, I can obtain that. But the matter of what speed you run, you can determine by using the chart that was supplied with your videotape. You may have noticed that there's one other handle on the apron of the lathe, which is this one. I have not talked about it as yet. When you move this handle up, you engage a set of clasp nuts which grasp the lead screw which drives the carriage. You cannot engage the power feed through the clutch and the lead screw, this handle at the same time. There is an interlock system in the apron that prevents that from happening for a very good reason. When you engage this one and the clasp nuts close, you'll find that the carriage travels at a higher rate of speed than it does when you go through the clutch. The reason for that is that this handle is used only when you're doing thread cutting on the lathe. Thread cutting is a rather specialized topic. I'm not going to try to cover it today. It's a specialized form of turning, and this has been covered in another videotape in this series, which you may wish to obtain if you feel like doing that type of operation. The tailstock of the lathe matches exactly in center height against the headstock so that you can support work on it, as we've shown you. It's controlled by a handle here, which is removable. It's a nut. It's a wrench that goes on a nut here. This frees the tailstock from the bed so that you can slide it back and forth. And when this is locked in position, you can use this handle to advance the ram. The ram is calibrated in inches on the top, which is very nice when you're doing drilling work because it permits you to drill to a known fixed depth. At the present time, I have a dead center in the tailstock, and you notice as I turn the ram back, it reaches a point where it pushes the center out. This is a normal condition for that center. It helps you to remove the piece from the taper. The tapers are hard to extract otherwise, and this takes care of it for you. The main tool that's used with the tailstock is the tailstock drill chuck. It's on a Morse taper, which you insert and you press in, and now it's firmly held. You can put center drills or twist drills or reamers in this to make accurate holes in whatever your workpiece happens to be. And you do that by cranking the handle forward or cranking it back, and when you've finished your work, you bring it all the way back and it automatically pushes the chuck out for you. When you take your turning cuts and your facing cuts on the lathe, which is the way we're going to begin making the boring bar holder, there's a preferred direction that the tool should travel. This applies to all turning and facing cuts, and I want you to notice that the cut should be taken toward the headstock when you're taking a turning cut. You back the tool off when you back it off, when you're returning the carriage to make a second pass, and you cut toward the headstock. Sometimes it happens that you have a special shoulder that you're trying to machine or something, and you will cut toward the tailstock, but that's a relatively small part of lathe operation in which you do that. The facing cut also has a preferred direction of travel. The way you normally take a facing cut is to run the cross slide in so that it's just short of the center of the workpiece. You lock the carriage in that position by tightening the lock. Then you feed the tool very gently into the work. When the tool begins to contact the work and begins to lift the chip, you advance the cross slide so that you finish off toward the center, which is just a very small dimension, and then you begin to feed the cross slide out from the center. This gives the smoothest cut, and in each case you want the tool positioned so that it has a slight angle to the work and it makes a slightly dragging motion. I have the diamond tool holder set up in the open-sided tool post. This is a very solid one, and this is the tooling that we're going to use as we get into making the boring bar holder. The piece of steel from which I'm going to make the body of the boring bar holder is a rather long one, so I'm going to support one end of it in this 3-jaw chuck. The outer end I'm going to support in the steady rest so that I can take a facing cut. I can bring up my tailstock drill chuck, make a center drilled spot in the center. Then I can remove the steady rest and support the workpiece on the center of the lathe so that we will have completed the requirement in each case of having the workpiece very firmly supported. The steady rest will support the workpiece firmly while we take the facing cut. The tailstock center will support the workpiece very firmly while we take a turning cut on the outside to bring it to dimension. I have already set this tool very accurately to the center height of the lathe, and I'm going to show you how I did that, although I have already done it. It will come up into position exactly where we want it to be. The tip of the tool which in this case is the diamond-shaped tool, wants to be exactly on the center line because that's where it's going to be doing the cutting. So to check that position, I've put a fixed center in the headstock of the lathe, and I carefully advance the carriage toward it. I move the cross slide to bring the tool close to the center line of the lathe, and I bring the pieces very close together. And you'll notice that the cutting tip of the tool is just against the center of the lathe. It's exactly on the center height. When you begin to cut a facing cut, the alignment shows up exactly, because if you have the tool set too low, you'll find that there's an unturned portion at the center. If you have the tool set too high, you'll find that the tool passes over the center and it leaves a tapered spot at the center. So these are the things that you look for. If you see an unturned cylinder at the center, you know your tool is set too low. If you see an unturned taper at the center, like a little cone sticking out, you'll know that the tool is set too high. But this tool, I have set it before and I know exactly where it is. It's right on the mark. Sometimes you have a workpiece on the headstock in a chuck or something that you're working on, and you still want to set a new tool for a new operation. There's no reason why you can't put the tailstock center in and turn the tool post, compare against the tailstock center, because in a lathe that's absolutely set up right, the tailstock center and the headstock center are exactly in line with one another, and they determine the axis of rotation for the lathe. Now we're going to set up with our steady rest and get the workpiece ready to take a facing cut across the end. Now I'm all set up to begin turning the boring bar holder, and I would like you to review a couple of the things that I've done here. To begin with, I've got the belt set for a direct drive on the head of the lathe, which is going to give me the correct speed. The second thing I've done is to mount my workpiece very securely. One end of it is carried in the 3-jaw chuck, which is a very solid, firm mounting. The other end is being supported by the 3-point steady rest, which is also a very solid mounting. When you set your steady rest up, it's necessary that you get it on the lathe axis so the workpiece is truly horizontal. The steady rest that I'm using here, I have small ball bearings on the tips of the jaws so that they can run directly on this surface and will support it correctly. If you have plain jaws on your steady rest, be sure that you put oil on this point, because otherwise you'll wear your steady rest out very quickly. And you remember from the previous discussion that I have the tip of the lathe tool exactly on center. So now in order to proceed with the cut, I'll bring the carriage back so that the tool just clears the end, and then I run the cross slide across so that I'm just short of the center. When I get it into that position, the next thing that I want to do is lock the cross slide in position so that it can't move. Now I'll advance the tool toward the headstock by using the handle on the compound rest, and I'll advance it just a very little bit so it just barely touches at the beginning. It's just touching. Now I'm going to put some cutting oil on the end of the work to keep the tool cool as it cuts the steel. Now the first thing I'm going to do, because I'm just short of the center line of the workpiece, I'm going to feed the tool toward the center line so that we cut that surface, and then I'm going to bring it all the way back to cut off the face on the front of the steel bar. The steel rod had been saw cut on the end, so it was not exactly straight. So I'm going to take a second pass to finish off and make a very smooth surface. I back the tool up a little bit, feed it in. I'll put the cutting oil on the work once again. Now you probably noticed while I was cutting what a nice continuous chip rolled off. When you see a continuous curling chip like that, it tells you that you have set everything properly. You have the tool set at the right height, you have the tool shaped properly, you have the tool sharpened properly, you have the workpiece supported properly, and you have it all running at the right speed. The quality of the chip almost always will tell you if something is wrong. If you see the chip beginning to break up into small pieces, it means that your tool is probably not in the right spot or it's not properly sharpened. If you see a chatter pattern developing, it usually tells you that you're running the lathe at too high a speed and you should slow it down. So one of the things you want to watch for is that nice continuously curling chip, because that is an indicator that everything is fine the way it belongs. Now with the workpiece supported the way it is in the 3-point steady rest, it would be possible to take a turning cut here. What we want to do is remove the surface to bring this down to the correct diameter and to get rid of all this rough corroded material. But we only want a short piece because the boring bar holder is not very tall and the steady rest interferes. So what we're going to do is make a center drilled mark in the end of the work, and we'll be able to support this end of the rod on a dead center in the tailstock. The way I've done this is that I've put a drill chuck in the tailstock. I have a large center drill in the tailstock drill chuck, and I'm going to advance toward the head to center drill the end. Now you begin by putting a little cutting oil on the workpiece and a little bit on the tool, and you bring the tailstock up until the tool is just about touching the work. Lock the tailstock in position, and now you can turn it on and drill forward. The tool starts in slowly, don't force it, let it go in, and as it's a large one, so as it goes in you'll begin to see the chips improve, and as we get up to the flared part of the center drill, you'll see that it will cut more smoothly and more quickly. Now we have a good solid seat drilled into the end of the workpiece. When you use a center drill in this way, there's one thing that you want to watch out for, and that is that you not drill too deeply. You want the sides of the hole to be tapered, so when you drill in, never drill into the second diameter on the center drill, otherwise your work will not be able to run properly on the tailstock center. You stop just short of that shoulder, which leaves you with a flared, tapered shape, and it leaves you with a small diameter hole at the center. The purpose for that hole at the center is that when you put in the oil, which you use, because this now has become a bearing when you put it on the tailstock, you put oil in there, the small part forms a reservoir which holds the oil and guarantees the lubrication of the workpiece as it runs. Now at this point, I've taken the steady rest off of the lathe, and I've put a dead center in the tailstock of the lathe. The dead center will go right into the tapered hole that we made with a center drill, but be sure that you put some oil in that. Sometimes grease is used, either a good heavy grade of oil or a grease. Either one will do the job satisfactorily. Clamp the tailstock securely in place and run the center in. Now you don't want that to be a real hard press in there, but you want it to be firm. You don't want any movement, because this completes one of our conditions for doing good turning work, that the workpiece is supported very securely. It's firmly mounted in the jaws of the three-jaw chuck. It's firmly supported out here on the tailstock dead center. In making this cut, I'm going to put the lathe on its power feed mode so that it will take the cut automatically. And the way I do that is to bring the carriage back by hand, and I feed the tool in until I'm just beginning to contact the work. Then I back the tool back a little farther so it comes just clear of the end. Now I have to decide what depth of cut I want to take. I know I have a keen tool, I know I have it properly positioned, and I know that I have the lathe running at the proper speed. I've engaged the appropriate gears in the gearbox at the end of the lathe. I've brought this lever up, which will actuate the longitudinal feed, and all I have to do to make it go is turn the lathe on and engage the clutch. So I'm going to take about 10/1000ths of an inch off on my first pass. That'll give me a chance to see how the cut goes and to be sure that everything is good. Now I'm not going to cut the entire workpiece, because I know that I need approximately 2 inches to make the boring bar holder. So I'm going to machine about the first 2 inches to get it down to diameter and remove all of the bad surface. There should be some cutting while on the work, and I do that with the brush as I turn the machine on. And now I'm all ready to take the cut. I can engage the clutch, and as the machine runs, you'll see the carriage go forward and the tool will begin to make its cut. Notice that the chips are coming off in nice continuous curls, which tells us that the work is properly supported, the lathe is running at the right speed, the tool is at the right height, the tool is properly shaped, and the tool is good and sharp. You can see just a trace of smoke coming up from my cutting oil, which shows that it's doing its work. It's cooling the tool down and keeping a good clean surface as the tool cuts. Sometimes when you're taking a long cut, particularly if it's on a thin piece of hard material, you'll find that the workpiece will heat up, and of course it expands. If that happens, you may begin to get some binding at the center point, in which you may have to make an adjustment during the cut so you don't have too much pressure at this point. In this particular cut, we're not removing very much metal, and we have a large workpiece which can absorb the heat, so we're not going to have that problem develop. Now I've turned enough of the surface to be able to make the body of the boring bar holder. So I'll disengage the clutch, which stops the advancing of the tool, and I back the tool away from the work. Now I can stop the lathe, and I can check the diameter with a caliper or a micrometer, either one. The diameter of the tool holder is not a critical dimension, so we don't have to work to a very precise tolerance on it. I'm going to use a vernier caliper to check the diameter of the work. This could be done with a micrometer if it were a very accurate part. But this is, we're about 1.6 inches, which is a little bit larger than the drawing calls for. The drawing calls for 1.5. But this is quite acceptable because it will simply give a little more beef to the work. So we're going to accept it at this point as being adequate to make the boring bar holder. We have to determine where to cut this off. This could be done with a cut-off tool, but in a piece this large, there is a chance of breaking the tool, and it may become a frustrating thing. So I think it's best to cut this off with a saw, either a hacksaw or a power bandsaw if you have one, and then you'll take a facing cut on the end where you saw it off. The important question is to determine exactly what length you want to cut off, and I'm going to show you how to measure that. At the present time, the workpiece can be completely removed from the tailstock center and from the chuck in order to cut this off. Now, as you look at your drawing, which shows the parts for the boring bar holder, you notice that in the boring bar holder itself, the part for which we've just roughed out the steel turning, there's a dimension which is marked as center height. This permits you to adjust the size of your boring bar holder to fit whatever lathe you happen to have. And the way you determine this is to put a center point in the headstock of your lathe and run the carriage forward so that it comes just under it, because this is the surface where you're going to mount the boring bar holder. Then you can use your 6-inch scale to measure the distance between the top of the compound rest and the exact center of the center point. On this particular lathe, it's approximately 1 1/16 inches. If you add that to the 5/8 inch dimension, which is shown on the drawing, this tells you exactly how long a piece you should cut for making the boring bar holder. One thing that you should keep in mind is that the end which has the center drilled spot in it was faced off and turned in basically in one setting on the lathe, which means that that end is very square and very true to the turned body. Preserve the identity of that end so that that will be the part that stands on the top of your compound rest. That will give you the greatest accuracy. When you cut it off to whatever length you need, in this case it's 1 1/16 inch plus 5/8 inch, which is approximately 1 11/16 or 1 3/4 of an inch. Mount the workpiece with that true flat end firmly against the body of your 3-jaw chuck. Take a facing cut, And that piece, that's all of the lathe work that has to be done in turning and facing on that particular piece. You notice that there are 3 holes. 2 are long holes which clear the clamping bolts. Go to the drill press, mark the locations of those holes, start them with a center drill, and drill them through to 0.266 dimension, which is approximately a 64th of an inch greater than a 1/4 inch. And when you've done that, you're prepared to go on to the next stage in preparing your boring bar holder. You can see that I have the workpiece all ready to go now. This is the body of the boring bar holder. You can see my center drilled spot at the center. I actually used that as a reference when I located the 2 holes which clear the clamping bolts. This was the original end that we faced off on the 3-point steady rest. I put it in the jaws of the 3-jaw chuck in this position and faced off this end so that I have a nice true end on each side, and the piece is a proper length to make my boring bar holder. I have the clamping piece all made up and the clamping bolts, and you remember we were using this center drilled mark to preserve the identity of the bottom, because this will be very true and square. And we just slip that in place, and we slip it into position on the compound rest. That's the way it will work when we're actually using it as a boring bar holder. Put washers on top and nuts, 1/4 inch 20 nuts. Use a wrench to tighten it down. You want it to be sitting fairly firmly at this point, because we're going to put the hole through it next where the boring bar goes through, and there will be some stress in doing that cut. So we put it down like that. Now the next thing we have to do is center this, because we want the hole to go through exactly on center. And the easiest way to do that is to put the center point in the headstock of the lathe and bring the cross slide over till it's in approximate position. Bring it forward, and as you sight across the top of the workpiece, you'll see the concentric circles where the facing cut was made, and you can align those by eye with the center point in the headstock, and you can move that into a very close position so that the hole will be made through the center. We're going to do the hole right on the lathe by drilling. Now there I have it very closely aligned. It's the center line through this workpiece is coming right over the center point. That this is all in line. We have to switch over to collets now. I like to use collets for this kind of a drilling operation because they hold the drills very truly and very firmly. And I'm going to be running the lathe a little faster than I did for the turning cuts, because these are small holes that I'm drilling, so it needs to be run a little faster. You'll notice I've put the belt over to the middle step on the cone so the spindle runs more quickly. I've put the collets in the headstock of the lathe, and I have a 1/4 inch collet in place. I'm using a 1/4 inch diameter center drill, although that's not critical. I've locked the carriage to the bed, and I'm going to advance the work by turning the handle on the compound. This way we'll go in so that the center drill begins to make its mark and to cut a passage where the boring bar will go in. In using the center drill in this case, you want to cut fairly deeply. You can go beyond the taper because this gives a very firm socket where the next drill will start in. Now I've used a 1/4 inch center drill, and I'm going to switch over to a 1/4 inch twist drill to pilot the hole through. The procedure that I'm going to follow in putting the hole all the way through now is to use a 1/4 inch drill, which will pilot the hole. Then I'll open it up a little bit at a time. I'll go from the 1/4 inch to a 3/8 inch drill, and I'll finish it out with a 1/2 inch drill, and I'll use the collets for holding the drills all the way through. Be sure that you use a little bit of cutting oil on your drill to keep it cutting cool, and run your lathe at about the right speed, and use the feed on the compound rest to advance the work into the drill. Back off once in a while to allow the chips to clear, and that gives you a chance to put a little fresh oil on with the brush. The deeper you get, the greater the need is for the oil to keep the drill cool. Now the tool is just beginning to break through this side of the work. Now we have the hole all the way through. Now we back off and we'll change to a 3/8 inch drill, and then we'll follow that up with a 1/2 inch drill. Now I've changed over to the 3/8 inch drill, and I'm ready to put the rest of the hole through with this size. This will cut very quickly because it has the pilot hole through it already. See what I'm doing here by placing that boring bar holder on the place where it's going to work on the lathe and cutting the hole in position. I've guaranteed that that hole is exactly on the center line of the lathe. It's exactly where it wants to be for doing the very best quality work. So that drill went through very quickly. Now we change to a 1/2 inch drill, and this part of the job is finished. We're all set for the final pass, which is with a 1/2 inch drill, and we'll bring the hole up to full size. Once again, we use the cutting oil. The workpiece will be hot at this point because we've been drilling fast, so be careful as you take it off. And you'll find some burrs around the edge of the hole. That's natural. So all you have to do at this point is remove the workpiece from the compound rest and use your deburring tool to clear up the edges of the holes. And this part of the tool is ready to go to work. The drawing that came with your videotape showed 2 different boring bars that you can make now to go in the boring bar holder. One is a small one, which allows you to reach into small drill holes to bore them out. The other is a larger one for working on larger work. Obviously the larger one will be stiffer and stronger than the small one, less subject to bending, so you can select the boring bar you want to use by the choice of the work. The dimensions given on the drawing are very good dimensions. They're very useful. They're the sizes that I have in this one. The boring bars go into place like this. You notice that there's a small turn down area here in the shank. That's where this set screw goes in to hold the boring bar in place. And either bar fits this same boring bar holder. I made the boring bars from ordinary 1/2 inch diameter steel stock. And at this point, we've gone fully through the operations of facing and turning, so I'm sure you can face off the ends of your rod by holding it in a 1/2 inch diameter collet and get them to the exact length you want, and take a small turning cut with a pointed tool to form this undercut. This is an important thing because the set screw will scar the metal a little bit, and if you don't make the undercut, they'll jam in the holder and you'll have difficulty moving them around or getting them out. Now, I'm not going to go through all of the lathe procedures for turning and facing because we've done that in making this piece, but I am going to show you how to do cutoff work. Cutoff work is done with a flat tool which mounts on the compound rest. You must support your work very firmly. In this case, we're going to use the collet. And you must let one end of the work be free. You work close to the collet when you're doing cutoff work. You run your lathe very slowly, much more slowly than you do for ordinary turning work. Now I'm going to put this in and just make a sample cut with my cutoff holder to show you how it works. The tool that I'm holding in my hand here is a cutoff tool. You can see this is a very thin tool, which makes it a bit fragile, and one with which you must work carefully. It's sharpened on the side so it has a taper, and in sharpening it I grind only this surface, which leaves me with a very sharp cutting surface at the top. The cutoff tool usually requires that you have a special sort of a holder for it, and this is one which I've made for myself. It goes on the compound rest, very much the same as the boring holder that we're working on. And you want to be very careful when you put this on that the cutoff tool is exactly in line with the feed direction of the cross feed. You can check this against a faceplate, or you can check it against an indicator, or whatever way is easiest for you to get that exactly in line. When you get it in position, you have to tighten this down very solidly, because cutoff work is a very heavy cut. It stresses your lathe a good bit. You do the work slowly, and you run the lathe at a low speed. I have set the lathe in back gear so that the spindle will not be rotating very fast. I'm going to feed the work in by hand. I will advance the carriage, and I will lock it firmly in place on the lathe bed. You want to have a little overhang on the workpiece, but not very much. You want to be working very close to the collet of the chuck. You feed the tool in slowly, running at low speed, and you keep a lot of cutting oil on the cut while you're making the cut. If you feed the tool in too slowly, you begin to hear a chattering sound, and you know you should push it a little faster. If you push it too fast, you run the risk of breaking the tool. This is one operation in which you really should not use the power feed arrangements of your lathe. This really should be done by hand feeding, because in your hands you have the feeling of the cut, and you'll know most precisely where you are. Now I'm going to start the lathe, and I'm going to cut the end off. I'm not making a part, but this is the way you could put the rod in your collet and cut it to length to make your little boring bars. You can see there that the workpiece just dropped off the end. This is the part that I cut off. You can see the little pip at the center where it finished the cut. When this finishes, you have a nice flat surface, because this is really a form of a facing cut. Do it slowly. Do it with the lathe running at a low speed. Be sure your tool is exactly on center. This is one place where you cannot deviate from that. Be sure you keep the cut continually oiled as you do it. The cutting tools that you put into your boring bars stick out on this side toward the operator, And you make those from tool steel, and you grind them to have a shape which is just like a plain turning tool. You see, I have a longer one in the large bar. I have a short one in the small bar because that's consistent with the size of it. Like all other tool positioning, it's important that the cutting surface of the tool be exactly on the center height of the lathe. And I determine that, just as I do with the turning tool, by bringing it up and comparing it with the center point. Now you see the way this boring bar is made, you can rotate it in the holder so that you can raise that tool. Right now I have it way above the center point. You can rotate it down, and by moving its position you can get it adjusted so it's exactly on the center line of the lathe, and that's where you want it. When you get it there, tighten down on this set screw, which clamps on that recessed area on the bar, and you're ready to put this to work. Now I'm going to put a 3-jaw chuck on, and I have a flanged bushing, and I'm going to show you how to take a boring cut on it. Now I have the boring bar in the boring bar holder with the tool set very carefully on the center height of the lathe. I have my flanged bearing mounted very solidly in a 3-jaw chuck. I have selected the correct speed that I want the machine to run, and I've engaged the gears so that I can operate it on the power feed. The tool will feed in this direction, and as it goes in, it will remove a chip from the inside of the work and will make a nice clean bore. I bring it in and I check the position of the tool. As I want to increase the size of the cut, I have to move the tool back this way toward me. So I back it off. We'll take about a 1/10,000th of an inch cut on this pass. Bring it up close. Engage the clutch. And start the machine. You can see that we're getting a nice clean ribbon of chips coming out. We're boring a nice smooth surface on the inner surface of that flanged bearing. When the work goes deep enough, we stop the carriage, stop the machine, and back it off. And we have a nice clean surface on the inside. Now if I want to go further with machining this, you can see that the operations that I have left before me are exactly the ones that we've talked about. I have a turning cut, I have a facing cut, and as I'm doing the boring, which is my third cut, I'm taking an internal cut, an internal turning cut, or boring cut. So there are the 3 operations that you do on a lathe. Everything else is a variation of it. We've looked at cut-off work. When you get to the more advanced work of doing threading, whether it be internal or external, you'll find that internal threading is a specialized form of boring. External threading is a specialized form of turning. And working from these fundamentals, remembering to run your machine at the right speed, have your tools properly shaped and ground, having them properly set, and having your workpiece firmly and solidly mounted in a chuck, in a collet, in a steady rest, or between centers, you will always be able to produce quality work.